everyone. This is the part 2 of introducing the concept and principles of the effective stress, total stress, and the pore pressure. In the first lecture, in the part 1, as I'm going to remind it again, if you look at this figure, we had a soil which is with this blow particles is shown, and then if we say that the point A, point B, and point C, the groundwater at point A, it is exactly at that point. At point B, the water also, if we put a piezometer, it is at that point. So it means that for all these 3 points, there is no difference between the water pressure. So if we put also the piezometer at the point C, it will up to here, so the water goes up here. So all these 3 levels are the same, so there is no seepage in the soil happening. So just a very short reminder, at point A, the total stress, if we look at the total stress at point A, it is the weight of the soil or water. So it is the H1 times that gamma water, which is this one. At point C, it is the H1 gamma water, the first term, and then it is the Z times at the gamma for the soil. So if we say that it is the gamma saturation, it is in the soil. And then for point B, it is the H1 plus the total height. It is the H1 gamma water plus H2 gamma Z. The pore pressure also, it is easy, it is linear. We know that at the point A, it is the H1 because the water goes up to here. This is the H1 gamma water. And then at point C, it is the H1, it is this height, H1 plus Z, H1 plus Z gamma water. And point B, which is the piezometer goes up to here, which is this total height of H1 plus H2 gamma water. And if we reduce these 2 terms, H1, for example, gamma water minus H1 gamma water, we get the effective stress, or this one minus that one, we get Z gamma prime. In this situation, which there is no seepage, the effective stress cannot get 0, because there is no way to get the 0 effective stress except from the top of the soil, which doesn't matter. So in the middle or the bottom of the soil, we cannot get a effective stress of 0. But let's compare it with another situation. So here we had the water as told at the same level for all these 3 points. So if the situation is changed, so the water level is at A, yes, that's right, it is here the same as the first example, but the water level at the B, it goes up if we put a piezometer. How much it goes up? For example, with the height of H. So it means that if we have a water level at A, it is here, this one is A, and this one is B. So the difference between the point A and B is H. So based on that one, we can define a concept of the gradient. So the gradients means that the difference between the top and bottom of the soil, for example, which is the pore pressure difference, it is H, and divided between the distance between these 2 points, which is the H2. So this gradient is very important. It means that due to the higher pore pressure at point B, the water started to get a seepage toward this direction, and this make the soil lighter, and somehow it can make liquefaction in the soil. Let's calculate the effective total stress and pore pressure again at these 3 points. So if I come and change maybe the color to this one, so the total stress is not very different from the first one that we showed, which is the H1 gamma water at the point A. At C is the H1 gamma water, Z gamma saturation. So then this one, so they are similar to what we have in the seepage, but the pore pressure is changed here. Point A, we have the water height here, which is the H1 gamma water, which is easy to calculate. Then let's forget about the point C and look at the point B, because we know that at point B we have the h. At point C at the moment I don't know that. We know that it is in between A and B, but I don't know that how much is that. But then for point B we can say that at point B it is the total height, which is this one, which is h plus h1 and plus h2. So at point B, so the pore pressure is h1 plus h2 plus h times at the gamma water. So that was easy to calculate that one. The main difference with this one is that we don't have this additional h, because we have no additional height here compared to this example. So then we have this additional, and then it is easy. So if we just say that if I remove those things, then if it is linearly between these points and the other points is moving, and then if we say that at this point it is okay, if I just write this pore pressure U, pore pressure which is linearly changing. So if you have a data here which is h1 plus h2 plus h times at gamma water, and at one point we don't know, but at the other point we know that it is the h1 gamma water. So based on the same slope, if we say that this one is the this is the point A, this is the point B, and this is the point C, and this is the between point A and C, it is the Z. Sorry, this one is the C, and this one is the B. And between C and B, or from this one here, it is the H2. So it is easier to say that how we can calculate that one. So if we say that this is the alpha, so tangent alpha, it is the or you can say that this value, it's this from the mathematics, this value divided by that value, I mean that h1 gamma water divided by that value. Let's say that U at point B, I don't write it, so you can write it later. This one divided by that one equals to this one, it is the Z, divided by that one, which is H2. And if we put the UB, this value, and make it complete, then at point C we can calculate this value. So the value here, it can be calculated based on this relation. So this one divided by that one equals to this one divided by that one. Then we can say that if it is UC here, another relation you can write, UC divided, for example, by UB, this one equals to Z divided by sorry, this is yeah, it is Z divided by H2. This one for point A, it was there. And if we calculated that one, we come up with the point that it is calculated to that point. So it means that at the point of the C, the calculation shows that at this point, the pore water pressure is the U at point C is H1 plus Z plus, if we just make it a bit easier, H divided by H2 times Z. And I have told that before, this term can be written like as I. That's the reason that it is written in this book with the I. So then if we just make a subtraction of these two terms. This one minus that one gets 0, this one minus that one we get this, and this one minus that one get that one. So then in this situation, and against of the first situation with no seepage, it is possibility to have the vertical stress to the 0. So Z gamma prime can get equal to I Z gamma. And in this situation, I equals to gamma prime to gamma water. And we name it as the hydraulic gradient. It means that if the difference of the pore pressure, water pressure at this point B and point C, which is H, is high enough that make a seepage here, upward or downward, it doesn't matter, but mainly it is upward for the liquefaction. If make it up like that one, at some point it can get a vertical stress to the 0 and the soil can liquefy. And this is very important term that we should remember, that when the soil liquefies, it means that there is no possibility to take any loads, and the heave, settlement, or many other things can happen. In order to describe it in an easy example, in the part 3 of my lecture, I want to put two examples. One example is related to the situation that we have no seepage, and in the other example, I will put a easy example that shows the concept when we have a pore pressure difference between the point B and point A, and we have a leakage or the seepage at the system. So please follow the channel, and then in the part 3 you will see the 3 examples of this one, which will be basic for my another lecture, which I'm going to start with the settlement, consolidation, heave, and the stress distribution in the soil. Thanks for your attention.